Now let's perform analysis. So this is looking at the order of the scheme. Now let's look at the resolution of the scheme. Right? The order is actually a slightly different concept than the resolution. It's actually possible to design a very high order scheme with pretty poor resolutions. I mean so the resolution of the scheme relates to how a high frequency wave is going to be approximated. So if I have I being if I have u being e to the jkx, then my u prime is actually so let's actually say if my u prime is actually jk prime times e to the jkx, right? So this is actually my numerical approximation, right? So let's say my numerical approximation for the derivative is jk prime times e to the jkx. We know that if it's a perfect approximation, my j prime should be equal to k, right? But because it is not, let's assume it is a jk prime and figure out what k prime should be. And plugging this into the equation, we immediately see that we move all the jk primes to the move all the derivatives to the left hand side. Then we see that ui prime times 1 plus a quarter, which is these terms, times e to the jk delta x plus e to the j minus jk delta x would be equal to 3 over 4 times actually ui and we have e to the jk delta x minus e to the minus jk delta x divided by delta x. Right, and if this is jk prime of e to the jkx and the ui is actually e to the jkx, right, then this cancels and we can figure out that jk prime is going to be equal to the right hand side divided by the left hand side. So e to the jk delta x minus e to the minus jk delta x divided by sorry, I think we still have 3 over 4 divided by delta x times 1 plus e to the jk delta x plus e to the minus jk delta x over 4. So this is what my modified wave number is going to be. So let's actually compute it and see what it looks like. So jk modified k dx is going to be modified actually jk dx is equal to 3 over 4 times these guys 3 over 4 times exponential of 1j times k dx minus exponential of minus 1j times k dx divided by 1 plus 1 over 4 times, I think this plus this, just copy it over, plus, just to check, yeah, okay. So this is my modified wave number, and let's plot it. So first let's plot the imaginary component. This time I called it correctly. Okay, yeah, jk dx. All right. Sorry? So let's actually look at what they are. Did I calculate them correctly? Oh, my division has to be dot divide, right? Otherwise it thinks I'm trying to do matrix division. Okay, so let's plot this again. This is the modified wave number of my higher resolution scheme. And let's hold it on and plot the actual, and the axis equal. Right, so you can see that the scheme actually resolves a lot higher frequencies than what's previously plotted, right? So the blue line and the red line stays together for a much bigger portion of the frequency range. Okay, and this is the imaginary components, and I can also plot the real part of this. 0, right? So this is again a scheme with absolutely no numerical dissipation. Okay, and the dispersion would only occur over the higher frequency ranges. All right, so let's plug this into MATLAB and see what happens. So here I need to construct a linear system, right? The linear system would be let's actually the linear system would have 1 on the diagonals and 1/4, a quarter on the off diagonals. Okay, so it's actually equal to identity. So let's actually say n is the length of u. A is equal to identity of length n plus 1/4 times. Does MATLAB have the function rho? It's actually, is this correct? Or it's actually another function? Don't remember. Or is it shift? Actually, so yeah, so let's actually just coding with the regular way. So diag of 1's n minus 1 1, so that's our upper diagonal plus our lower diagonal, which is the same thing with minus 1 being the shift. So that A, let's try it. Let's see, n is equal to 4, and let's actually try it over here. My A would be, yes, the right thing, except for because I have a periodic domain, I need to fill this and this with a quantum, right? So I need to fill the A1 end is equal to 1/4 and A end 1 is equal to 1/4. So if I try it over here, yeah, right, so I have the right matrix. Okay, so that's my right hand side. I also have B, my right hand side being basically the central difference multiplied by 3/2, right? The central difference is ui plus 1 minus ui minus 1 divided by 2 delta x. So here I have a 3/4 as opposed to a half. So let's just use what we have for the central difference. B is equal to, instead of divide by 2 delta x, I have divide by delta x times 3/4. Okay, and the du dx is equal to a backslash b. So this is how I would use the higher resolution scheme. Now let's solve this, use our higher resolution scheme. And if you actually usually code it up, you wouldn't actually reconstruct the matrix at every step, right? You have constructed the matrix and use that matrix A for every step. So you wouldn't, I mean, the performance would actually be a lot better than what seems to be indicated over here. And another thing to note is that if you actually have coded up this high resolution scheme, it's actually more useful to use implicit time stepping as opposed to explicit time stepping as what's in OD45. Because in every time step, you have to solve a matrix system anyway. So if you actually work out the math of plugging in this high resolution scheme into a implicit time stepping, for example, an implicit Runge-Kutta or a backward difference scheme, you would only have to solve the linear system once that serves the purpose both for the implicit time stepping and for solving for this higher resolution scheme. Kind of starts to wonder if I put in too much of n. So this is actually, well, let's actually make a smaller n to be 100. Set this. Oh, actually this to this, and let's solve this with less grid points. And close all and plot my U transpose and see. That's too much to end. Okay, so this is basically how my high resolution scheme is dealing with the square wave with only 100 grid points. So as opposed to being completely messed up, this is the 100 grid point solution is kind of similar to the central scheme with about 1,000 grid points, right? So we can see that it actually helps a lot. Still, this has absolutely no numerical dissipation, so all the dispersions are kept and shown over here. All right, any questions? Okay, so this class we have talked a lot about the finite difference. Basically, this is a more advanced version of the finite difference we talked about. And starting from next class, we are going to be looking at now finite volume schemes of how to improve the resolution of finite volume schemes. So previously we only discussed actually first order finite volume schemes that can resolve shock waves. Whenever we go higher order, like second order, the scheme starts to have problem dealing with shock waves. So next class, we're going to be talking about how do we make a finite difference higher than first order and still able to resolve shock waves. All right. And about the custom project, the proposal is due today, and I'm going to be holding an office hour today. I think we're going to send an email very soon, but the tentative time is from 1 to 2:30 in my office. If you want to talk about the proposal, come over. All right.